हो ठीक आहे. हो. सोर्स आता फक्त स्पीकरमध्ये स्पीकर व्हिडिओ फुल करायचा आहे. शेअर स्क्रीनमध्ये शेअर व्हिडिओ फुल करायचा, स्पीकर व्हिडिओ झीरो करायचा आहे. ठीक आहे. हो हो हो. Yeah. Hello everyone. Myself Mrunmayee Deshpande from Antariksh team, Vishwakarma Institute's Pune. I welcome you all to this fourth session, the YouTube live series that we are taking. I'll welcome you all to this session. Today we have with us Dr. Bhooshan Gadre. He is currently a postdoctorate fellow at the Max Planck Institute, Germany. His current research work like includes creating models based on gravitation models for fast gravitational waves detection and using them to categorize the binary black holes. He has done his PhD from IUCAA in 2018, wherein he uh, wherein his thesis work was on detection methods for the gravitational waves, which is very quite interesting. Now I'll request Dr. Bhushan to address the audience. Thank you. Sir, sir, you're live.
So, hi, I am Bhushan. So, I will talk to you today about gravitational waves, which I know we have heard so many times. But today, I am trying to go in some more depth than general, more public talk because I think this is for all engineering people. So, why not? So, this is the title of my talk, Symphony in Cacophony. Of course, I am talking about symphony is gravitational waves, cacophony is everything else, which is noise, which helps us not to detect gravitational waves. And I guess I can start. Yeah, Yeah, me. So, me. So, yeah, going ahead with what I'm going to talk about. Yeah. So, uh, so I'm Bhushan. As you already know, I am a postdoctoral researcher at Albert Einstein Institute in Germany. And so today I'm talking to you on behalf of Antariksh Club about gravitational wave detection. So this is what we have so far from O1 and O2. So O stands for observational runs of LIGO and Virgo detectors for gravitational wave signals. And from first two runs, we have here more than 10 gravitational wave signals. And we can see here that on the right column of each panel, we have what we call periodogram or frequencygram, where the x-axis is time and y-axis is frequency. So it is time frequency map. And in the second column for each of the signal, we see a gravitational waveform, which is reconstructed by different things. So there are some changes, and you see some broad patterns instead of single line for waveform. The interesting part is now we have just finished O3. Of course, it finished early because of Corona. What can we do? But we have 40 plus more such a gravitational wave events. So it is going to be very exciting. And well, in year or so, we are hoping to start O4. So it will be running more gravitational wave signals, I guess. Yeah. So plan of the talk is very simple. I will start from what we call as train data, which gravitational wave detectors like LIGO, Virgo, or upcoming LIGO-India see, which is this blue whatever noise that is plotted there. Then we have gravitational wave signals modeled assuming general relativity and some dynamics, and that signal looks like this. So initial part is called in spiral, which we can approximate better. Then there is a part in the blue which is called merger, which is when black holes are very close to each other, and then we have to model them using numerical relativity because analytical or semi-analytical methods do not work. And in the end, when black holes merge, they form a single object, but it is not yet settled. So it still emits some gravitational wave signal and settles down. What I want to tell you is, given these two, how we come to the conclusion shown in the bottom two panels. So on the right, we have graveyard, what we call, because we have all the black holes, neutron stars as their masses. And these kind of arrows shows that these two black holes merge to form higher mass single black hole, which is at the top because of course it is heavier. And on the left, we see the value estimated by LIGO or the gravitational wave events by like using gravitational events by LIGO to estimate Hubble parameter. I'm sure you have heard in a couple of talks ago by Swagat that Hubble parameter is the constant which gives us the speed of galaxies farther away. So they are moving much faster away from us. So this is propensity constant measurement. And there are many different ways to measure this. So we have Planck, Shoes measurement, and now we also can do it with gravitational wave event. So let's go ahead. Let's talk about longest antenna through which we see the signal, which is of course LIGO Virgo detectors. So we know they are interferometric detectors. They are complex nonlinear systems, so they have many independent components, and all these independent components are responsible for introduction of noise, including our own things like flying aeroplane. Then there is train, the fracking, mining. Those things happen around the detector. Everything contributes to the noise, which we call anthropogenic noise. But because these components are independent, using central limit theorem, we can approximate this noise as a Gaussian noise. And remember, I'm giving this introduction, but my plan of the talk here is to go into some more depth than what you have already heard in public or popularization talks. So I will walk you to what actually we do in data analysis. So these are just precursors to know which assumptions we make and why. So this is a usual video you have must have seen many times how LIGO detectors work. Well, it shoots the laser as it is shown. It split into two by a beam splitter. It travels to arms of LIGO and comes back. And what is measured is change in phase or path difference of these detectors, and we measure it, or we measure constructive or destructive interference to see if there is a change in length. And this works as op amp or differential amplifier, and that's how we detect the signal. So if signal is present, here we have see exaggerated arm length changes, but reality they are very tiny, which are more than million times smaller than the size of the atom or size of even atomic nucleus, thousand times smaller than that. So this is a miracle which we see. But anyway, so this is just how it works. And like any radio telescope you heard last week, we also have antenna pattern or directional dependence of how sources look. And these pictures show how antenna pattern function looks like for different directions in the sky for current locations of LIGO and Virgo detectors. And the last patch also includes India and Kagra. And we can see the numbers close to 1 are good because there we can see, and which are red and yellow, and numbers close to blue or violet are bad because there we cannot see gravitational waves. So if we have more detector, we can cover more sky. So that's why we need more, a network of more detectors, and that's why we are having LIGO India. So let's see, what do we mean by cacophony? So I don't know whether you will hear this sound very carefully, but I will give you some other references in the end where you can actually understand the talk and title of this video even better. But you can see, listen to this noise coming, right? Yeah. This is all LIGO data converted to uh, our uh, to different music or say cacophony so that we can listen to it. And this is all the noise which we see in the data. Just precursor to understand what that is, what we heard. Let's recap the Gaussian distribution or Gaussian probability distribution. So if x is any random variable, then its probability density for Gaussian or normal distribution is given by its width, which is given by sigma, and also its mean, which is mu, and it is exponential square is given by this particular formula. For LIGO, we usually assume mu 0, and that's why this plot here. And why is this important? As a precursor, it will become clear in a minute. So, as I was saying, what we just listen come from LIGO Virgo data. And as I mentioned a couple of slides before, we assume that LIGO data is Gaussian and stationary. Well, what does stationary mean? Stationary means its probability distribution, where even if we move in time, it does not change, and it actually changes very slowly. So for our current searches, for which signals last for order of minute or seconds at max, so this is okay. And just to give some mathematical notations or details, so this train data we usually work in frequency domain. So we use Fourier transform. I guess all engineering people are aware of what Fourier transform is. So I'm not explaining more. For people who don't know, it is just a way of converting time domain data to frequency domain, and we can equivalently work in frequency domain instead of time domain. And because our LIGO data is, or we assume it is stationary and Gaussian, The probability distribution for this turns out to be very simple. So we have mean zero as I already mentioned, but sigma, that is the standard deviation or width of the distribution for each frequency, becomes linearly independent, and then each frequency acts as independent random variable with variance or width which is given by PSD or power spectral density. And how it is defined? Given this formula, it is or Gaussian distribution definition is trivial. So what Sn of f or PSD is? Well, it is defined here like this. So it is ensemble average of many noise realization and its power. So the name should be very clear. It is power because it is square. It is spectral because it is frequency dependent, which you can see here. It is density because this is at per unit time per unit frequency beam. So that's where the name comes from. And I guess many engineering people, or at least who are working in data analysis, must be aware of white noise, where this have uh, it means if gravitational wave with frequency 100 have this particular amplitude which we can detect it, but if the same thing happened for frequency of 1000, that we cannot measure because this is not above this PhD. Now moving forward, as I for cacophony, there are many noise sources present, and those are shown here. And we can see here the one noise source which is missing, which is anthropogenic noise, which is noise which we create. But that's what I wanted to know when I say cacophony. So all these things actually gives us problems, and that's why we, which I'm sure you definitely have heard, and some additional music which people have put on it to make it like more symphony. Yeah. But what are these events? So the pulse, which you heard. But when we say these compact binary mergers or CBCs, so question is where do they come from? And these compact binaries are binary black holes, binary neutron stars or neutron star black holes. And there are two broad channels through which they form. So one on the left is called secular evolution, where two usual stars actually they are in binary, they evolve together, they go supernova, die, they form either neutron star or black hole, they come closer and they merge, and that's what we listen to using LIGO. Another thing is there are independent many stars which die and form black hole neutron stars, and then they collide with many different black holes in the dense environment. Then there are multiple interactions. They go through various channels, and they finally this two of them stick together and merge to form one. And we can also detect these. The interesting part about these two formation channels that they more or less have a peculiar property. So secular channel have more or less circular orbit and spins which are parallel to the total or orbital angular momentum. And otherwise in dynamical capture, the orbits can be very eccentric because this happens just because of just random capture. And the spins can be aligned anyway. They need not be aligned in the orbital angular momentum or along anything. And that's why whole orbit can precess like a top. So how we characterize these compact binaries? So there are total 17 parameters, but we are currently ignoring eccentricity and looking at circular orbit. So the whole system can be characterized by 15 parameters. So component masses, these are two parameters. Then both black holes or neutron stars spin. So their spin is vector quantity. So they have another six parameters. Then we don't know their orbital phase or their time when they will coalesce or collide. So these two other parameters. We don't know their sky location, that is where they are in the sky and what is their distance from us. And also we don't know the orbital orientation. So orbit is in plane if they are not precessing, but how they are oriented. And polarization is similar to electromagnetic waves, as electromagnetic waves have two polarizations. So gravitational wave, and they are called plus and cross. So here in the picture you can see various frames. So red is our LIGO detector which are on the ground. Then there is another frame in blue which actually wave frame. So this is gravitational wave coming from the source. And then this green frame denotes actual source frame, and ellipse represents an orbit. And we can see they can be oriented anyway. So inclination is this angle I, and polarization is given by this angle psi with respect to detector. And then there is some more orientation parameters which are given here by theta and phi. So we need all these parameters for full analysis, but let's see what we do. So for that, how we model gravitational signal? As I said, we have general relativity, and gravity is anyway very weak force, and we know that already when we compare it to electromagnetism or any other strong force, nuclear forces, everything. And the reason is this coupling constant, which has value of 10 raised to minus 44, which is very small. So at any instant given any system, we can get how much gravitational waves will come out based on double time derivative of moment of inertia of this system. This is called as quadrupole formula, and this is quadrupole. Similarly, for electromagnetic dipole antenna, you have here dipole, and here instead of mass density, you usually have current density. For electromagnetism or charge density, and but this is at one instant, and when we want to model the source, we have to evolve the source, and as it emits this gravitational wave, orbit will shrink and they come to close to each other, and so everything else will change as conservation of energy, momentum, and angular momentum. So we have to evolve all this quantity. So R denotes actually the evolution of the actual black holes in center of mass units. Then P is momentum, which is mv. So you can see this is like how their position changes, how their velocity changes, and this is how their actually spins change. So spins also undergo changes, and we model it in many different ways. So let's see what happens and how we actually model this signal. So here is a simulation of two black holes which are going around, and this big arrow actually denotes orbital angular momentum, and small arrows denote their individual spins. We can see quadrupolar pattern forming below, and we can see gravitational waves emitted or how they will look below in the panel. This is how we model actual gravitational wave, and you can see precession of the orbit, that orbital angular momentum is moving around, so their spins are changing. So we have everything which we need. Now let's see what we can do to detect these signals in this pretty noise. Well, just started for detection. Again, as I mentioned, that strain data is Gaussian, and PSD act as a least count for that particular frequency. And what I mean by that, it is explained here by slightly bad plot. Sorry about that. But you can see here three events, their strain amplitude plotted against these noise PSDs for two different detectors. Here also we have noise from Virgo, PSD from Virgo, but we are not looking at Virgo right now because it has lower sensitivity. But yeah, so we can see here this particular event is right above. So this is very loud and clear event. So the other, and we already know this is very loud and clear event because blue one is the first detection event which was loudest, and then there are other two events which had very low SNR, so that we can see here. So SNR is more or less area under the curve here, and how that is we will come to it. So given this, we have LIGO data and we want to find where the signal is in all this data. And how we do that? Well, for that we use statistics, something what is known as hypothesis testing. And hypothesis testing is very simple, that we put up two hypotheses. One is called H naught. I don't know why it is H naught and H1, but that's how it is. So first hypothesis, we say there is no gravitational waves data or signal. The data is just a noise. And the alternative or H1 hypothesis is, well, there is some gravitational wave signal happening at particular time t with particular parameters vector theta. So this theta includes all the 15 parameters which I mentioned a couple of slides ago for this particular event, and that particular signal is present in the data. Now, given the strain data S, we wanted to know which two of these is true, knowing that the LIGO noise without any signal is more or less Gaussian with the given PSD as it widths for each frequency. So, how we do that? Well, if we know there is no signal, then data should be just noise which has Gaussian distribution. So probability distribution for that data can be given by a simple exponential square formula. What is this bracket? We will come to it later, but just think of it as some kind of inner product or square. If H1 is true, that is some gravitational wave signal is present, then we know if we subtract that signal out, then the distribution of whatever leftover strain, which is S minus H, should be just noise, and it should follow Gaussian distribution. So we have both of these formulas. Now we need some method to find out if there is some signal present or not. So for that, what we use is something called as maximum likelihood, which is nothing but the ratio of these two probability distribution. And it is obvious. If probability of not signal is very low and the probability of high signal is very high, so ratio will be high, and we will more confidently able to say that there is some signal. And when we take the ratio of these two, so this divided by this, we get formula which is this, and only first part of it is called as a match filter. Why it is called match filter? It will become clear in a minute in the next slide. But before moving ahead, I would like to talk about hypothesis testing, or how this particular maximum likelihood quantity we will use to see whether there is a gravitational wave signal present or not with some confidence. So let's look at this particular plot which is coming from hypothesis testing. So this plot actually shows the probability distributions for two hypotheses. So one on the left is coming from H naught, and this is for H1, of course. And well, if there is a signal, then we will have these values somewhere here. Let's say maximum likelihood value somewhere here. So there is some probability that it is coming from signal, because this value can come from signal because signal distribution is here. And there is also some probability that this value may come from the noisy data and not real signal. So we are trying to infer something here, but while inferring, we can make different kinds of error. What are those errors? There can be signal and we still say that there is no gravitational wave signal, and that is one kind of error. And there may be actual gravitational wave signal, But still, we may infer that there is no gravitational wave signal, it is just noise, it is another kind of error. And those two errors are plotted here. And what I mean by that? So let's look at this. So suppose this is the statistics value which I got, and these are some representation of these likelihood quantities. Then what I know that if I just do this ratio from noise, I will get this quantity. And I do this ratio for multiple different ensembles and I take the distribution, I get this another quantity called H1. If I choose this value as determining threshold, then I will miss those signals and I will say them. So I'm taking this mean value here or whatever this vertical line as the value. If the value of my likelihood greater than this value, then I will say signal is present. If value is less than this, then I will say there is no signal, it is just noise. And because this distribution overlap like this, I can say sometimes just noise, I will still infer that there is a signal and vice versa. I may miss few signals just because of this threshold. And we can change this particular threshold to fine tune our searches. So for that, coming from this particular statistics, we define this particular SNR. We are not going through whole derivation, and this is the reason it is called match filter. We actually match this whole signal against the data, and if this pattern match with some pattern in the data, we actually recover large values or SNRs, and that's why it is called match filter. We usually use normalized template h1 equal to 1. This helps us in not worrying about this last term, which we ignore for match filter statistics. And as I mentioned, this rho naught is this particular quantity. So if this SNR or signal to noise ratio is greater than some quantity, then we say there is signal. And yes, we have detected signal with this parameter. If the SNR value is less than our threshold, then we say, well, H1 is false and H0 is true and there is no gravitational signal. Well, this we have done only for parameter theta, but when we actually search over LIGO data, we don't really know what parameters, what masses, what spin, what location in the sky, when. This is not like laboratory where I can make some black hole and ask it to collide now and I can just observe. They can collide anywhere in the sky, anytime with any masses. So I, in principle, have to search over all the possible parameter space or all the possible parameters which we are looking for. These are just some details that you currently search for non-precessing or just uh, align spin cases using circular gravitational waveform. There are various reasons why we do that, and we are not going into those because that will become even more technical. And we use Fourier transform to search over time quickly, and then we have to go over all the parameters. We cannot change the parameters continuously because that is infinite search and we can't do that given finite computation. So we then discretize and search over the parameter space, and that's what we call as a template bank. And oh, sorry. Uh, okay, I forgot to put the picture of template bank. That is fine, but we search discretely over the parameter space. Now, exactly how this match filtering works, this is just a quick demo of that. We see here is a data, there is a buried signal which is not visible to naked eye. But when this model gravitational waveform actually correlates with that signal, we get a nice cross correlation peak in the LIGO data. Let's go over it again quickly. We can see when this particular signal which is present in the data in red matches with this signal, we get peak there, and this is what happens. So we look for the peak in the data, and we do it for all the different discrete parameters which are millions. So before doing this, we need to precondition data. I guess the simplest way to explain this to engineers is to say the words and put one simple picture. Band pass, I think everybody know what that is. So we low pass and high pass the data, and blue is the original data for which contains all the frequencies. Then we high pass about 20 hertz usually, and we low pass below 2 kilohertz, and then we get the green data, which looks much nice Gaussian. There are no low frequency loud oscillations, they are removed. Then there are no jitters, which are high frequency, they are removed, and we are left with very clean data, which is green. So which is first requirement. Then, as I said, that LIGO data is more or less Gaussian, but not completely. There are some transient glitches like this present in the data. So here we can see some gravitational wave signal and then glitch present there. So to remove this, what we have to do is condition data further. And for that, what we do is we get this data. And how we do that? So here is example of gating. So this particular loud artifact is present in this particular data, and we just gate it. So the shape of the gate is shown here. So this is particular shape of gate, and this is needed to, so we don't get any numerical artifact in the noise, and we clean data that way, and we make this data zero with some windowing, so it goes to zero smoothly. And how it improves the performance, let's see, if we haven't have removed this particular noise artifact from the data, the SNR values it gives us just because of that goes to thousands. And when we remove this particular things, we get the SNR values after getting, which are again in red. These values are around 5, 6, 10, which is what we expect from Gaussian noise. If these kind of values are present in the data, then it becomes very hard to see any gravitational wave present in the data. And why? We will come to it in a couple of slides. So back to match filter. We have clean data, removed unwanted glitches, what we call, or noise artifact. And this is how match filter over few seconds of data looks like. So we have one model gravitational wave signal. We matched it with data, three different data sets, LIGO, Virgo, and so both LIGOs and Virgo. And you can see signal to noise ratio is usually below 5 as expected from Gaussian noise. And there are some cases where the signal is much louder. The one case is here. And here there is a true event, so which is 170814 event particular. And we have zoomed around that event for half a second. And what we see here is all the three detectors actually show peak with very small time delay. And this is what we call coincidence search. So we not only search for signal in each detector separately, but when we want to claim some signal as a real gravitational wave event, we demand that signal with the same parameter should present in the LIGO detector simultaneously with some delay of less than half second or something. So exact parameter is 15 milliseconds, but that is different. And we can see here for true signal, there is actually peak coming from same template, that is same parameters, which have SNR much above what we call a background or other things where there is no gravitational wave signal. Now, again, going back to this, what we are doing, so we have to search over all the parameters like we have seen here just for one particular template which matches to this signal which is present in the data. But understand that if we use all the other templates, we will just get things like this without these peaks which are present for all other parameters which we will search with, because that signal will not match with the data. And as I said, we search over masses, spins, sky position, time, etc. And searching over time is done by going through all the data which is present here. I'm just showing you just few seconds of data, but we have years and years of data. And this is the template bank I was talking about earlier. So here you can see the x and y axis are masses m1 and m2, and then different colors say different components. So these are binary neutron star, then this is NSBH, neutron star black holes, and these are black holes. And these are couple of earlier events which are detected. So which templates or parameters this event corresponds to in the template bank. Now what we do is we get all this data which looks like this noise. Now how to make the sense of it? How will we call something as a detection? So for that, we to decide row naught to claim a detection, we use some statistical term called as false alarm rate. And what is that? The name is obvious, that is false alarm rate. So false alarm is when we actually say that there is signal when there is no signal. Or quickly going back to this plot. So false alarm is type 1 error. So we say there is a signal even though there is no signal. And this is what is called false alarm rate. And rate is just per unit time or per unit something. So for that we use per year or per second false alarm rate. And how we get that false alarm rate? Well, we literally count coincident events per year in the data we observe. So suppose we have data of 5 years, we count all the events and we divide by 5 to get just per year number. And how we count these coincidences? Well, going back to this plot, so we have this kind of plots for all the templates or each point in this template bank. What we do is for same template in the data for each of the detector, we count how many events at particular SNR value we have captured. And that is what is plotted here. So event with the same parameter or same template have less than 10 or 15 milliseconds delay are called as true gravitational wave signal or foreground. And then which have or the signals which match but have time delay greater than 100 milliseconds. So we know gravitational wave travel at the speed of light more or less. So if there is more time delay, then we know that is not a real signal, but this is just a noise behaving like a signal and giving us some particular values. And what we do is we just plot these two values as a cumulative histogram. That is just number count less than particular value. And this is the plot from the first detection paper. And what this plot present is, say value 12. So this curve says how many events are there which has values greater than 12. So that is what cumulative thing is. So here we can say there are 10 raised to minus 6 of these events per year coming from just noise because we are looking at the background. And when it is true event, those comes out to be like this. And we know there will be always some true events which have very low signal to noise ratio or SNR. And we don't claim detection for these because they have very low SNR. We cannot say anything. For detection, we have to have false alarm rate low enough. So we usually go for 1 per year, 1 per 10 year, or in this case, as it was first gravitational detection, we went bit overboard and we wanted false alarm rate of 1 per 10,000 year, or that is equivalent to 5 sigma number, which is present here. What does that mean? Suppose there was no gravitational wave event occurring anywhere in the universe, and we kept our LIGO detectors on and observing for 10,000 years. Then there is a one chance that there is a possibility that once we will get event above SNR of something like 14, which is given by 5 sigma, only one chance by noise. And we see here the first detection actually have SNR of more than 23. So we are clear that the false alarm rate is definitely more than 10,000 years, but we cannot estimate it because it will require lot of data and computation, and we don't need that. So we are pretty sure that it is actual a gravitational wave event. And we do this for every gravitational wave event. Now, going into somewhat detail, what it means by having these two backgrounds, what is in black and what is in violet. Well, if there is this true event present in the detector, so what I mean by is this loud peak, and it will match and give you high statistical value even with this number here, because this particular value is coming from actual event and matching with the noise. So that is not noise only event. That is event coming from signal and noise. So we want to remove it once we know there is something which is real. And then the points in this astrophysical background, which corresponds to this particular event time or this particular time around this 10 milliseconds, we remove them and we just count remaining literal events which are coming from the background as false alarm rate. And this gives much better estimation of the gravitational wave background. As I was saying, we do the same thing for each of these events, and we have detected plethora or variety of events. Just let's take a point or take a minute to see all the different events and try to understand there are these different x-axis times. So this is here 40 millisecond, 40-second long signal. Here signals for binary black holes are less than second or 1 second long. They are loud, less loud. Like here, they some look very good, some not that much. But for each of this event, we go through all the method which I have just talked about, and we detected all this with good enough false alarm rate. That is false alarm rate greater than something which is quoted when we look at all the detections. Yeah. Yes. Now, given this, now we have recovered the symphony. Now we want to know about better about characterizing the events or what they mean by each of these events. So this is another cartoon. Just listen to all the symphony and notes here going around, and then merge. And each of that sound which we saw actually correspond or tells about the various parameters or property of each of these events. So how we do that? Now in years of data, we found out where particular interesting GW signals are in all that data. Now what we do is called parameter estimation, or for that what we use is Bayesian inference method. And why we do it only after searching or detecting rational wave events? Because Bayesian inference requires us for each of these events to model these gravitational waveforms many million times and calculate different values. and that is computationally really very expensive. So that's why we use template banks and search using only aligned spin templates, circular orbits. And once we know where there are signals, we throw kitchen sink at it and do whatever we can to find out more about these particular signals. And as I mentioned, this analysis requires millions of CPU hours. So we burn down a lot of supercomputers and use a lot of energy, which is bad for environment, but we don't know better ways. So you are welcome to help us there. So what is Bayesian inference? So for that we use the chance we get that particular kind of data is likelihood, which we saw before. Then phi of theta is a prior probability of obtaining that particular theta. So we may not have any prior knowledge about what we are looking for, or through electromagnetic observations, we may know or look for what kind of event we are looking at, and we may have some prior information. And P of D is just a probability prior with the likelihood which we calculate from the data, which is this prior, and then we multiply it with the likelihood quantity which we observe here. And then for particular parameter theta, we get the distribution for around its true value. So we don't know actual value of the parameter theta, but we know value lies somewhere between say -2 and 3 to 6 or to 8, and that's how the probability distribution for that particular parameter looks like. So this is one dimensional posterior. In reality, we have 15 dimensional posteriors or even more dimensional posteriors here, which we look at and how they look like. This is what they look like. So the top left panel show the posterior distribution around masses in M1 and M2. So we never measure actual exact value for match because that is impossible. But we know true value of mass lie somewhere here for this particular event. So different colors and plots show different quantities, and different contours. Dotted lines show Q, which is different mass ratios, which is the lower mass divided by upper mass. So different mass ratios. This panel, which is top right, actually shows us final mass and final spin amplitude. And what is this? When two black holes, when they merge and form the final black hole, it has some mass, which is final mass, and it has some spin or angular momentum, which is given by, or magnitude of it is given by final spin. So we can infer this also. So these are posteriors for this. And similarly, this is chi effective, which is just measurement of spin, and chi p, which is measurement of precession. I'm not going into detail to explain these plots, what they are, but this is what we measure. So these are actually priors and posteriors, which are plotted here. So on the left, there are priors, on the right, there are posteriors. So you know what likelihood values we have got here. Similarly, we can actually infer chirp mass, another parameter, and distance. And distance can give us redshift Z, which you must have heard, and this gives us about information about Hubble parameter. So again, we came to Hubble parameter by looking at all these different sources. And this is just results from O1, O2, and more on the way. Also, as per I know, in the next week, you will know how these gravitational wave observations and other electromagnetic observations actually go hand in hand very well and provide us even more information. Just before we finish, I just want to tell you that what we talked about is like optical astronomy when Galileo or Newton made their first optical telescope, which were not great. So we are in this particular frequency range with LIGO and first gravitational detection. But the gravitational spectrum is all over here. So here there are radios, infrareds, then X-rays, gamma rays, and UV. all these spectrums for gravitational waves, we have yet to see what is happening there. So these are different instruments. You may have heard of LISA, PTA, SKM. You must have heard last week. Square kilometer array, which is radio telescope. You can use that also for gravitational wave detection. Then these are DESIGO, which search in DC hertz or DC hertz frequency range. These are other detectors, and these are different sources which we can find there, which we know of, and we don't know what we find which we haven't found before at all. So this is new frontier and adventure, and how you people fit in, apart from people who are interested in astronomy but also from engineering perspective, is here. So this is courtesy of Professor Tarun Sarodip, who is now at ISER Pune. So LIGO-India connects to all these different areas of physics and engineering and education together. So if you are interested in all these different engineering aspects which are in red and orange, or interested in computing and data which are here in violet, or if you are interested in any kind of physics or astronomy, we all can come together and learn and take this opportunity. And please do join us for LIGO India. And thank you.
We had a really great talk, sir. The chat box was flooded with comments, questions, and discussions. This was really a successful talk. We have selected a few questions that I would like to ask you. The first question is by Vijay Chavan. He's asking what makes them assume the signals to be Gaussian. In the in the first slides, we have selected a few questions that I would like to ask you. The first question is by Vijay Chavan. He's asking what makes them assume the signals to be Gaussian. In the first slides, we have selected a few questions that I would like to ask you. The first question is by Vijay Chavan. He's asking what makes them assume the signals to be Gaussian. In the first slides, we have selected a few questions.
Hi, sorry, I'm getting some kind of feedback here. So, question I'm hearing multiple times, I guess. So, I will take that question until we fix that. So, we don't assume signals to be Gaussian. We assume data to be Gaussian and not signals. Signals are like whatever these waveforms looks like. And why we assume data to be Gaussian? The reason is uh, many independent noise sources, as I mentioned here. So with central limit theorem, so LIGO Virgo has many complex systems which are nonlinear and work together, and they come up as independent noise sources. There are some correlations, but then we can just count and consider independent noise sources and talk about those. And there are still many. So usually central limit theorem assumes more than few tens or hundred sources, but we have few hundred or even more stochastic sources which give us Gaussian noise, which is of course slowly time varying. But at first order, when we clean data, as I have mentioned, we usually it is good enough assumptions for 99% of time to assume that data is Gaussian. Mrunmai, I am not hearing any questions here, so I don't know if you are speaking.
yes, sir. Just a minute. Yeah, there were some glitches earlier. Fixed it. Yeah. The next question that is from Astro Explorer. It is a two-part question. First of all, he's asking how many gravitational wave templates have been created till now, like approximate number. Next question that is from Astro Explorer. It is a two-part question. First of all, he's asking how many gravitational wave templates have been created till now, like approximate number.
Yeah, okay. Okay, so we actually have in currently for O3, we use a template bank which is of the size of 500,000 templates, 500,000 templates, and that is just for the masses which are less than 400, from 1 to 400 solar masses. If we and align spin, if we want to search over all the other masses and spins, template number of templates can go into billions. And it's not like we cannot model all those multiple templates. We can, and we do. In fact, we try to do better and better modeling always using numerical ability and everything, but it is still computationally hard to search over all of them.
Okay, so the next part of the question includes what if we get a signal from unknown source and the correlation doesn't match with any of the template?
I'm still getting your questions also with some delay. I don't know why.
I There's some issue in the system, I guess. Did you get the question?
Well, unmodeled signals, which look for essentially the same kind of signal which appear simultaneously in at two or more detectors. So these signals we may not know them or we may not able to model them before, but if they are loud enough, then we should still able to see them.
Yes, sir, definitely got it. The next question I would like to ask is what are the software simulations, the simulation that you showed earlier, what are the softwares used? Like, can we access those? What are the software simulations, the simulation that you showed earlier, what are the softwares used? Like, can we access those?
Yes, indeed. So if you go to the video description, I have asked organizers to put them a lot of different links for different softwares used, different tutorials, how you can do different things. Also, first two links in the description are the links which will take you to the sound of space, and if you go through those links, the second link will take you to many more black hole simulations where you will see the waveform and can listen to them. When I decided title and abstract for the talk, after that I came across that particular web page, which is excellent. So people do also look at that, and all the softwares which are used are also mentioned in LIGO data pages or web pages. And I guess I have shared links to many of them in the description. So you will get those there.
We'll definitely get through those links. Thank you. The next question is by Akshata Saraswat. She's asking, does harmonics of gravitational waves play any role in the detection of the gravitational waves? If yes, how?
Yeah, this is excellent question. Uh, for most of the events we expect based on our knowledge of gravitational wave signals, we expect only quadrupolar, that is dominant harmonic or mode, to emit most of the power. So lower order modes usually don't play much of a role in actually detection. But of course, in parameter estimation, it does play a bigger role. because then it helps us to narrow down sky locations or polarization, some other parameters like that. Or if signals are precession or if there is eccentricity and other stuff involved, then a higher mode can have more and more power. Or if we look at the sources which future space-based mission like Lisa, which will going to fly in 35 or something, will detect, their higher modes are absolutely essential to do any kind of study. But for most of the vanilla LIGO sources, they are not that important. But for heavy sources or with heavy mass ratios, they can definitely become very important.
Certainly, we'll get a clearer picture. The next question that I would like to ask is how you measure the distance z of a source in the gravitational wave detection.
Uh, it's yeah. So I don't have any slide ready for this, but usually, I guess I have. Is yeah, sorry, yeah, I don't have anything I was looking for. But usually, if we look at the strain signal, the amplitude and strength of the signal which we can detect based on not only the signal parameter which go in this quadrupole, but also distance from us where they are. So we usually see distance depending on the orientation of the signal or how they are and everything. But we can definitely measure the signal based on SNR. The simplest way is suppose we pin down the masses and then we know if that particular SNR is present in the particular area in the sky. So for that, these antenna patterns, okay, where are they? Play a bigger role. Okay, I can't find antenna pattern functions, but the masses, the distance, and antenna patterns, or where they are in the sky, can actually give us the sense of location. Where they are, can I find antenna pattern functions? Ah, I seem to have lost them. Oh yeah, yes. So look at this plot. If we know that signal is coming from this particular red region in the sky, then we know that we almost recover all the power emitted by gravitational wave in that region. Then, when we know the masses and all other parameters, we can pin down the distance very well. Now, if they are coming from these regions which are bluish, then we know there is large uncertainties in what we are measuring. Also, we are seeing here are the combined net detector pattern. But if signal is coming from different regions in the sky, like one here, we know that one detector may have sensitivity of 80% while other may have sensitivity of 100%. Then we know depending on their ratio where they are coming from in the sky, and that also help us pin down the distances. There are of course many degeneracies like inclination and other things which will still be there in determining distance, but that's the best what we can do.
Certainly, the answer is sufficient. The next question that I would like to ask is does supernova also produce some gravitational waves rather than shock waves?
Yes, there are predictions or people have done simulations, what we call in supernova modeling, and supernova will emit gravitational signal. As the quadrupole formula I was showing is definitely generic. It has nothing to do with what kind of signal we are looking at or anything. Any kind of change in quadrupole moment, which is defined here by mass distribution. If it changes with time or its acceleration, as there is second derivative with time, we will get gravitational waves. And people are trying to model these gravitational waves. The only problem is they are not as strong as binary black holes or binary neutron stars. So unless and until there is supernova very close by in our own galaxy, we cannot detect them.
This was definitely new for most of the people. I'll take last two questions now because you are already over time. The next question is how do you guys calibrate different observatories across the globe? For example, LIGO, Virgo calibration process.
So this is question better answered by my colleagues who actually work on detectors hands-on. So uh, I take this as calibration for each of the detector. So what we actually measure, like the video showed, is the laser power on photodiode, which is converted to voltage, and then there is lot of calibration which actually happens to convert that voltage to gravitational wave strain data which we see, and that uncertainties in that also are taken into account when we actually do parameter estimation and all other analysis, which I guess you should hear from somebody who is expert on detectors and not somebody who is expert on astrophysics.
Definitely, sir. One last question is by Nishant Pawar. He's asking if the gravitational waves passes through a blind spot of one of the detector, but is detected in the other detector. So how does this kind of signals analyzed, and what is the credibility of the signal? How is it checked?
Yeah, very good question. So we are actually trying to figure out how to do this even right now for O3. We don't have very clear answer, but we know some templates which we call clean templates, which are much longer, like binary neutron stars or that kind of template. We know the transients or glitches in the detector are very short duration of order of second. So when we know there is and we see some clear track, right, which we can see for the gravitational wave signals, then we know that uh, so these kind of tracks, if we can see very clearly, then we can say there is a signal more or less. But these kind of signals, if present in only one of the detectors, which do not show clear chirp like this long flaws, but just something like this, which can be coming from the noise artifacts, then we can't say with very good certainty that it is actually true event. So in that case, we definitely miss those signals. We try to take into account as much as from them with some probability that it may be true or it may come from noise, but that's what we do. And that's why we need network of many detectors. So there will be at least few detectors looking everywhere in the sky.
That was definitely insightful. Zamir sir is about to ask a question. We'll just wait for him a minute. Really sorry for the delay.
That is fine. I'm just saying sorry to our viewers or who is listening. I'm not very good with sitting at one place very quietly and not moving around a lot. So
That can be troublesome.
apologies for that anyway. I'm not looking at my video, so I don't know what I'm doing anyway.
Yes, sir, the video and the content is really very nice. We will review it later if you need.
Yeah, sure.
Thanks, Bhushan.
Yes.
खरंच भारी टॉक होता. It was really wonderful talk.
So do you have questions or we are live or not? Or what?
We will go off. Yeah, there are many questions even I have, and I wanted to ask, but I can't go ahead with so many questions here. So, like, what your suggestions about like for the students like who are pursuing from engineering background or science background? So,
Uh, so I can tell you what I think. So as far as I know, I have worked with three, four engineering students who are actually working in astrophysics kind of sense. So some are in Ayuka, some at some other places. And if they want to do astrophysics, then they definitely have to learn more about physics and astronomy. But apart from that, keeping more with what engineers have learned or with what engineers know best. We already know, or you know better, maybe, Zamir, that we already know need more mechanical engineers, electrical and electronics engineers in building LIGO. So uh, they will get definitely some interesting projects or work to do for LIGO India. So they should approach LIGO people with sincere and clear proposals to what kind of project they can do and what they want to do, what the expertise they have, and they can do some very good projects then. And I think people should also know about something called LIGO sub program, through which people can actually go to different LIGO sites and work there. I am not the I don't know lot of details about it, or I don't even know uh, how to apply or what happens, but people can look it up for post Corona projects.
sure, definitely, like we will guide students what you have said, and whatever I know, definitely will share with the students. And thanks for the content and links and resources what you have shared with us. And it was really wonderful talk, and we're really thankful to you.
Okay. So you for organizing and inviting me for the talk. Thanks for you, Antariksh Club, and again Mumbai and Vedang. I don't remember his names or people are organizing behind the scene. Thank you, all of them. So, yeah. So
Thank you
all,
very much.
all of you.